Great. Perfect. Thanks, Vish. Yeah. So let me just start off by thanking the organisers for this wonderful workshop. It's always lovely to be in this part of the country, and tomorrow into the park is always something special, along with fantastic talks. Otherwise, I'm really looking forward to the week. So what I'd like to talk to you about tonight is some results that we have in the computation of Nielsen complexity for superconformal primaries. That's primarily based on the two papers which I have on my today, the one with Robert Korp and Mika Kim, and the other with Woodsel Rabambi, also known as Teflon Rabambi for those that know him well. So what I just want to start off with is just the motivation of why this is something that we're interested in studying and how it fits into the original theme of this workshop. So the notion of complexity is conjectured to be related to black hole dynamics. More specifically, the growth of complexity is conjectured to be equal to the growth of black hole interiors. And the Philosophical double is a famous example of this, where as you increase the entanglement between the two CFTs, you increase the wormhole volume, and this wormhole volume is conjectured to be equivalent to complexity. So the entanglement in that sense is the complexity. Now, this is of course in the high energy physics motivation field. There's also motivation as an interesting quantity in its own right, and then there's a diagnostic of quantum chaos. So you should think of this as a diagnostic that supplements such measures as the spectral form factor at the time, or the correlated Boschman echo. And the cartoon sketch of what one should expect is essentially that complexity for a chaotic system. So in a Hilbert space, the vast majority of states are at maximal complexity for that system. So for a chaotic system that evolves ergodically throughout the Hilbert space, you'd expect it to be saturated at maximal complexity or approximately saturated for a very long time. Whereas for an integrable system, you can expect that there will be a rise in complexity, but that it should plateau around the maximum complexity for a much shorter time, because the number of states that explore that's explored in Hilbert space is much less than that of a chaotic system. One thing that I just want to point out, and that's also highlighted in this paper, is that behavior that you see for the chaotic system requires the development of conjugate points on the complexity manifold. That's going to be just a small point that's going to be relevant for the discussion later. Okay, so having said that, let me just start defining what is meant by complexity, specifically Nielsen complexity. So the rough idea of complexity is to measure how hard it is to synthesize a desired target state from a particular set of gates at your disposal. So you have a simple initial state, a reference state, you have some set of unitary operations that you can perform on the state to eventually reach a target state. And you want to measure with a metric, that's notated in G there, how hard it is to obtain that state. So some unitaries might be more difficult to apply than others. So as an extremely simple example, consider this case where you have 3 unitary gates, U1, U2, and U3, and you can obtain a target state with 2 different combinations of these unitaries. And now the state on the left-hand side and the right-hand side give you the same target state, but the one on the left-hand side you say is it's fewer operations. It's about a total of 8 unitary operations, so we can assign a complexity of 8 to it in a particularly simple choice of measure for that. And so the right-hand side produces the same target state, but you have to do more work. So it's not the most efficient amount of work that you have to do, so the complexity is the smallest number of unitaries that you need to apply in this case. This is a discrete notion of complexity. That's closely related to what we would imagine in quantum computational setups, where you have really a circuit and some unitary gates inside that circuit, and you apply them to your input qubit a discrete number of times. But for Nielsen complexity, we will be interested in continuous notions of complexity. One of the primary reasons for this is just to simplify the problem. We can do more analytic computations with these continuous notions of complexity. And the idea is to take the accessible gates to be from some chosen symmetry. So as a simple example, consider issue 2, where you've got the 3 issue 2 generators, and you can act with that, any member of that family of unitaries on your reference state. So here I've got, for example, the accessible target states. In the case of issue 2, they'll be labeled by 3 real coordinates. and you obtain them by acting on the reference state with an arbitrary element from that issue group. And now what you can do with this is, well, you obtain a manifold of target states, and you can impose some metric on this manifold of target states.
So what is U of S1, dot Sn?
So this would be for a general unitary group, and you have n generators of that group, and so that would be the real coordinates exponentiating those generators to obtain an arbitrary element of the group.
So, but how many gates are both there?
So you should think of this as you have access to the full unitary group as the set of gates. So this is why it goes from a discrete notion to a continuous notion of complexity. So from this group, you can select any one of the unitaries at your disposal to obtain a target state. I have not yet specified the metric that's going to be important in defining complexity for this exactly. But yes, so you have this idea that we're going to have a metric, and the shortest distance on this manifold of target states is defined to be the complexity. And you can introduce some certain parameter, usually sigma, running from 0 to 1, taking you from the reference to the target state. And you would usually choose this to be along some geodesic on this manifold. So two examples of metrics that are commonly used in the literature, assuming that all unitary transformations for this group are equally hard to perform, is the F1 cost function. So we have this. There should be an absolute value sign on the right hand side, but we take the absolute value of this expectation value of the unitary derivative of the unitary with respect to these little coordinates that you have. That's the F1 cost function. And of particular relevance for this talk is the Fibonacci metric. So we have this particular combination of these unitary operators, take the expectation value with respect to the reference state, and this defines your metric on this manifold of target states. A very nice feature of the Fibonacci metric is that the group symmetries are encoded as isometries of the metric. So if you started off with the issue 2 group, then you have issue 2 isometries in the resulting metric space in this case. So I'm just going to rewrite this slightly, and that's going to be important for the explicit computations of this. You can rewrite both of these two cost functions in the following way, as overlap of these target states labeled with different coordinates. So the F1 cost function, for example, you can write it as that overlap, take a derivative, remember that is u dagger du, so it's that derivative acting on the target state, and then setting the coordinates equal to one another. So that's something that you can do. And for the Fs metric, you take the logarithm of that overlap, take those two derivatives, set the coordinates equal to one another, and you obtain the Fs metric. And the reason this last one is of particular relevance is that any normalization factor of the states factors out completely. So any normalization factor of the Fs metric, any overall phase of those states do not contribute to the metric at all.
So just n is the dimension of the group.
Sorry?
The n is the dimension of the group.
That's right, yes, exactly that. Exactly that. But in the Fs metric states that differ by an overall phase identified at the same point on the manifold. It's the distance between them is 0. And this overlap, this u dagger labeled by the S prime coordinates, u with the S coordinates, this overlap is a key quantity. And in fact, what that is nothing else than a generalized coherent state of the group with that given reference state, as studied by Campbell, for example. So what we're really interested in is computing these coherent state overlaps, and they source the relevant metrics for the Nielsen complexity. And now, from the known literature on these coherent states, there is an important subset of generators that's important, known as the stability subgroup. And this is a group of generators that acts on the reference state to produce an overall phase. And these, on the Fibonacci metric, are not going to contribute to it. So these generators do not matter, and the choice of reference state is quite important. You can make a choice of reference state such as the stability subgroup is quite large, which gives rise to a much simpler Fibonacci metric. And for Fibonacci metric, there's a one-to-one mapping between the states on the manifold and group elements of G factored out.
So why does the stability subgroup depend on the state that you are choosing?
It does, yes. So because of this third condition here, that you want the unitary acting on that reference state to be an overall phase. So an example of this would be in issue 2. you can pick an eigenstate of J0, for example, J3, and then J3 is in the stability cycle. But you could have chosen a state that's not an exact eigenstate, and then you wouldn't produce an overall phase. And you would get a direction associated with J3.
But at least in the SO case, which is I can simply imagine, there the stabilizer of any vector is just SOn minus 1.
Yes.
Right, so it seems quite confusing. I mean, you're saying it's T by H, so you want to get rid of the overall phase, but you also want to get rid of the overall norm, right?
That's right, yes.
Or these are unitary, so that's not something, but therefore it should be yes.
Yeah.
It seems you've basically done a CPN minus 1, and then the H is what? So you somehow take
so it's maybe if I could just use these two as an example. So you have again J3.
but what you normally have is that you have the block sphere, and that's CP1.
Yeah.
So therefore we're done. That's the state of the single qubit. It's the block sphere. So what more do I need to know?
So I might, so maybe, this doesn't just take it from discussions of available theory. Maybe I'm missing something. I agree with that statement, that that's the issue too. But I'm afraid I don't have a good answer for that at this stage, unfortunately. This is not going to be particularly relevant for this. This is just a comment on these given states. I'll have to revisit that if it's on the frame. Right, so that was the relevant background for this.
So, is the notion of locality somehow built into the method? Like, some set of generators are easy, or some. I mean, I understand that you write down this method, but is this sort of somehow like the notion of locality at all relevant here?
No, so in this case, we're assuming all the generators to be equally hard or equally easy to perform in this case from the code. There are definitions of complexity where this has been adjusted, but for our purposes, we are just going to be interested in the simplest case of computation.
So it's true. I mean, this scalar metric you had, I thought was it would be a very short distance if it happened that the unitary was near get in, as you would expect. It should be a short distance. So therefore, not all unitaries are equal. Right? Those that are near the unitary have small distance, and then as you build up far from the unitary, they have bigger distance.
Yes, I should adjust that statement that all the generators are equally easy to apply. My apologies, that's right. Yeah, so all the generators are equally simple. You don't have a different weight associated with each of those. That's right. So one of the points that I just want to flash for the purpose of this talk is what we've realized out of these computations is that Baker Campbell Hausdorff formulas can be used as powerful computational tools to compute these two units that are interesting. So, for example, just consider the SOD group 2, Euclidean conformal group, with relevant algebra. I think this would be very familiar with, and a paper that motivated us to look into these the cases of spinning and superconformal primaries is this paper by Shagner, Chapman, and Zakowski, where they studied the case of spinless conformal primaries. So understanding that it's just the eigen, so delta has some spinning primary, and it's annihilated by spinning L mu, as well as the special conformal generators, and there's some eigenvalue on the D. Now, how these Campbell-Hausdorff formulas come in is what we want to compute is something like this overlap. This is what we're interested in computing, e to the alpha dot k, e to the alpha dot p. The point being that D and L act trivially in this reference state. They produce at most an overall phase, it does not matter on the manifold. And what the Baker-Campbell-Hausdorff formula allows us to do is to swap the exponentials of these generators, roughly speaking. So you would have e to the alpha star dot k, e to the alpha dot p, and then there's a formula that allows you to exchange them so that p is on the left and k is on the right. And this is relevant because k annihilates the state Kent, whereas p annihilates the problem. So in other words, these two exponentials on the left and right will act trivially and some overlap. And you can now easily extract the relevant overlap that you're interested in. E to the d, alpha star, alpha.
So far you were interested in unitary groups.
That's right.
Now you're talking about the conformal group. Is that going to play the same role? Or it's some auxiliary structure?
So it's not necessarily unitary that we're interested in. So we're interested in a set of unitary operators chosen from some symmetry, which in this case would be SOD commutator.
Unitary operators in SOD commutator.
That's correct, yeah, that is correct. So, yeah, I might
But more like a
slightly
unitary
more
representation of SOD commutator.
Yeah. That's right. Alright, so this is the relevant overlap that you've computed using BCH. And when it comes to the computation of the spinning case, we need to do a little bit more work, but there is a BCH formula that we've managed to write down that, as far as we're aware, is not available in the literature. So, if it is available in the literature, it's something I'd really like to know. But this is something that we have checked to hyperturbative order that this works. So, the idea would be that we'll have an exponential of A times an exponential of B, and these two operators, and we want to exchange them in such a way that we get something that's like B on the left hand side and like A on the right hand side. And what I mean by that is that you can define these nested commutators. A and B, I take a commutator to define this operator C, and any balanced nested commutator containing equal numbers of A and B I define as Cn plus 1 depending on the number of A and number of B. And if you take an additional commutator with A, you get something from the A family of operators, and an additional commutator with B, and you get something from the B family of operators. Now, the key assumption for this formula to work is that any member of the A family commutes with each other, anyone from the B family commutes with each other, and anyone from the C family commutes with one another. Now, in this case, what we have found is that the following formula works. So you have the exponential of A, exponential of B, and you get on the right hand side this infinite product of these B family operators, C family operators, A family operators. Now this is not one that we've been able to prove, but we've managed to check this for up to 15A and 15B operators, up to that determined order. And in addition to this, this formula may look a bit hard to handle, but you can set up a recursive equation to solve for coefficients appearing in front of the different generators, and you can solve those equations with appropriate boundary conditions.
And you can't prove it just by recursion, no?
We've tried, but we may be missing a simple way to do it. But I suspect that a proof using recursion might be possible, yes. I suspect that may be possible. But the point is that you can use this to generate known BCH formulas for issue 1, issue 2, other ones from, for example, SO4.2 we've also reproduced. And those are ones that are going to be useful for the coherent state overlap that we'll compute later. And in addition to that, ones involving supersymmetry generators. Now, supersymmetry generators, you've got Grassmann variables, so these terminate at the finite order. So we know that this formula is also okay to use in that case, so we don't need to prove it explicitly from those. Checking it to a perturbative order is okay. But as I said, this is a formula that we expect to hold in general, having verified this up to up for 15 and 15 weeks. And I suspect that because of proof may be possible.
What causes the sign difference in AN plus 1 and BN plus 1?
Sorry.
So what causes AN plus 1 is A commutator CN and BN plus 1 is CN commutator B.
Oh yes.
What's the reason for that?
So there's not. You could have had the B also on the left hand side with an overall minus sign that sign appearing. This way is there's just an overall minus. I'm not sure if I'm answering the question correctly. But yes. So this is the formula at least. This is something that we would like to verify in the future. And so before I get to these explicit formulas, I'm just going to flash something I think many of you are more familiar with. That's just the spinner notation for these generators for SO4.2. We're interested in SO4.2, for conformal group, and 4 dimensions specifically. Within my applications to the ADS-CFT correspondence possibly. So of course you can introduce this spinner notation that makes the SO4 mapped into issue 2 cross issue 2 manifest. So you've got an alpha parameter and alpha dot parameter, both are transforming over issue 2. And in addition to these, you can include an index I that sums over these different species of superconformal. And the commutators of Q and Q bar gives you translation, and the conformal supercharge S bar and S give you a K. This is something that I think many of you will be familiar with, but just for the sake of completeness. And of course, the Latin indices transform under some R charge generator, so UN. So taken together, the superconformal group we're going to be interested in is SU2.2 /. So, of course, one thing that's just going to be a little bit later, again, I'm sure everyone's not familiar with this, is that the Q and Q bar increase the scaling dimension by half. And this is because you're mapping from bosonic states to fermionic states. And for fermionic states to bosonic states. Alright, so the circuits, so first just a comment on the reference state that you can choose. So the reference states you can choose to be an eigenstate of rotation, spinning operators, and the R-charge generators. These all commute with one another, so you can find the simultaneous eigenbases and specify them. And for the L generators, I'm just going to choose the eigenvalue to be represented by H and H1 in this case. So you can see that in some of the formulas coming up. So the circuits that we're interested in studying are similar to the ones that we saw for the scalar primaries previously, are these ones over here. We've taken an element from the group and you've acted with that on the reference state. And you've just taken out all the generators that act trivially on the reference state. The ones that either give you an overall phase or that give you an overall phase or a factor of 1. And so this is the remaining set of generators that we're interested in studying. And so the overlap that we want to compute is this one on the 4 line. So this overlap, this super coherent state overlap is what we want to compute. And on this formula that I flashed previously, we can use this sequentially, because there's, for the choice of A being A and B, where A is K and B is P, you get a set of BCH formulas for that after solving the recursion relation here. You get another one for Q and S, and another one for Q bar and S bar. So you get a set of rules. Sequentially, you need to swap these generators around, supplement this with other simple BCH formulas. So it turns into a bit of a bulky computation, but every bit of the step can be done analytically.
So the formula are commutators, right? That now have also anti-commutators, but that's...
Sorry, what's that?
I thought the formula only had commutators. But now they have also anti-commutators, but
yes,
so easy to handle with the parameters.
Yes, so the Q and S here are grasping variables in this case. So,
Okay, so then everything ends up in a commutator.
Exactly. So that's how I want this. I should have specified that. My apologies. Yes. So the Q and S here are grasping variables. That's why you just get commutators. And this formula that was derived below still holds, which was derived using commutators in this case.
The parameters are different, right?
Yes, so this is just for keeping track of the computation, but there should be complex conjugates or
Is it a norm or in a portion?
this will be in a right.
I mean, is the parameters different both? Because
Yeah,
you were
so-
talking about some S prime stuff and then S and S prime.
That's right.
Here
So,
also they're different, we look the same.
so for example, K alpha dot alpha should be P alpha alpha dot star. It's just this is just taken from in the paper. There's just a lot of coefficients moving around, and so it's just it makes for easier reading if they just give it their own name, but then just say that they are the conjugates of one another in this case. So the coefficients do look different, but they are related by complex conjugation in this case.
But then it's not in a part, then it's not.
Yes,
I mean, if the thing that does all the descendant on one side is the conjugate of the other, then it's a norm.
yes, there you go. Yes, it is.
But I thought you were interested in the element that depends on S here and the other bra which depends on the S prime. And then you want the inner product of S and S prime.
Yes, so maybe I jumped into that a little bit. So what you're going to do is, you're going to take the derivatives and then set those coordinates equal to one another. Equality in this case means that exactly that statement that, for example, K and P are complex conjugates of one another because they come from taking a group element with real generators and then decomposing that into these separate exponentials that you have. And that induces complex coordinates in general. So the P alpha alpha star is a combination of real coordinates combining into a complex coordinate in this case. So that's where that statement comes from. So just as an example, just in this notation of the spinors. So here's just an example with n is equal to 0. So this is a result that was known from the 2021 paper where we studied spinning around with no supersymmetry. And this is just to verify that the expression that you get out is the correct one. What's nice in the spinning notation is you can see there's this balance of the indices, as you would expect there should be, as well as you get the product of factors, each raised with the permanent complements in this case. And now what you have is that this is the product of terms. So when you take the logarithm to produce this Kähler potential that you want to take derivatives with respect to, this is going to be a sum of different terms, so a sum of different terms and some of them take. Now this is as far as we've got into the computation in this case. You can of course write in the complexity manifold, and the idea would be to solve the geodesic equation of this manifold and then complete the geodesic lengths. But this is not something that we have done yet. This is something that we hope to return to. And specifically, what we would be interested in is to study the emergence of conjugate points on these manifolds.
Emergence of what?
Conjugate points. What's this? So what that means is that you have a confluence of geodesics in the manifold. So again, the two spheres are a good example where you have two antipodal points. So these are conjugate points in the sense that you can follow a geodesic around the great circle until you reach the North Pole, and then there's a second geodesic, the other half of the great circle that meets again. So what happens in the case of complexity is that if you would evolve in time from, say, the South Pole as your starting point, then it would evolve and the complexity would increase until you hit this conjugate point, and then it would swap over to the other geodesic, and you would expect a decrease in the complexity. So for the case of n is equal to 1, of course you have a single RTL generator, and you can choose the reference state to be an eigenstate of that with some charge R. Unfortunately, the formula you get out is explicit, but it is quite bulky, unfortunately. We've tried simplifying this as much as we could, but this is as far as we could have gotten. You get the same sort of structure. So product of terms raised to the power of these quantum numbers, and when you take the logarithm, it will again give you the sum of that difference.
So you will see what we understand from this.
Yes, in the next slide. So there is one limit where we can make some progress in understanding what is happening here. And this we say two of the corresponding variables associated with q bar is bar to 0. But the structure you get out is exactly what you saw for the non-supersymmetric case. So just focus on the last line, for example. So in the first half of that, what we see is the sum of two terms. The one with scaling dimension delta plus h bar. So that is what we have for the non-symmetric case, or the non-supersymmetric case. And then added to that, with the four corresponding variables, you've got another one of that form with a scaling dimension of +1 added to it, which is exactly what you would expect. So these are from the bosonic two-point functions. You start with two bosons. One of the coordinates is inverted, and that gives you exactly the form that you have. And so you have the two bosons with scaling dimension differing by 1, and some multiplet. And then the bottom line what you have is something that looks a little bit different, but this is exactly the fermionic two-point function with one of the coordinates inverted. So in this limit, you do see exactly the kind of structure in this overlap that you would expect. And you get, if you send q and s to 0 as opposed to q bar and s bar to 0, you see exactly the same structure.
So I don't quite know what I expect. You said that I get something that I expect.
Oh, yes. So maybe, let me just, I don't have put this in the slide, but just going to make a quicker one.
Oh, I see. So is it basically taking the conformal primary that is living at origin and moving it around on the sphere, and then that's why it is becoming a two-point function? Is that how I should think about it geometrically? Because if I don't have this other stuff, just have the P at least, then that's what it would translate.
Yes, absolutely. Yeah, that is definitely a way that you can think about it. But the other crucial point is that so of course what you think of is you would have the difference of the coordinates. So you would have x prime minus x to some scalar dimension values. What you see in this case is something that looks a bit different to that. But what that is coming from is making a transformation of the one coordinate and converting it. So x goes to I think it's x over absolute value of x squared. There might be some things in this, but this is the graphical transformation that we're talking about. Inverting one of those points, and that gives you exactly this structure that you see in the denominator.
Where is the inversion happening? I mean, why is the inversion happening?
So this is something that I'm still hoping to understand, but I suspect it might be due to the fact that you've considered the Euclidean conformal group, and that might be the reason for it, but it's not something that I have a good understanding for yet, unfortunately. But if you go to the inversion for the Bosonic two-point function, you get exactly the terms of this form. If you do that for the fermionic two-point function, you get exactly this. So that is what's represented in this. And then there's an additional term for the spin of these primaries. Right, so for the energy 2 case, we've also computed these overlaps explicitly. Unfortunately, the formulas are quite bulky. We're hoping to simplify these a bit, but they are explicit using these H formulas again in overlaps. So this is still very much a work in progress in some respects. What we'd like to understand is the n is equal to 4 case. So these computations are underway, but there's just a lot more indices to manage. But we hope to get something in that regard soon. The key question we'd like to answer is whether these give rise to conjugate points. Or what is the role played by spin and supersymmetry in the development of these conjugate points in the manifold. And as you study these different quantum numbers, is there a difference between the small and large scaling dimensions for these? So, in terms of the development of conjugate points in the manifold, for example. I should just maybe add that these manifolds that you get might look quite complicated, but the symmetry is restricted immensely. For example, the scalar curvature of the spinning primary manifold it's a constant scalar curvature. And that scalar curvature is dependent on the choice of quantum numbers. That is just a short after-go talk that I have. Thank you for your attention, and just thank you for the relevant research contents. Yes.
You said on the last slide, comment about the curvatures. Do you know what the signs of the sectional curvatures on these manifolds are? Are they positive, negative, or zero?
I think this depends on the choice of quantum numbers. So this is why we're hopeful that there will be, at least for some choices of the parameters, the development of conjugate points. But computing this explicitly is still on the way.
What is the time scale at which you expect conjugate points to be?
Oh, so I know that in the literature it's in the exponential of the degrees of freedom of the system. I'm not sure how that translates into
It depends on the system. If, for example, in an integrable system, conjugate points can appear very quickly, polynomial in a number of degrees of freedom.
But and in the chaotic system, it's the exponential one. I see. Thank you for that.
Also, when you're saying it's conjugate points, one gets the idea that there's some kind of global discrete symmetry or something like that ensures that you have these geodesics come together again. But one would figure that if there was no discrete symmetry, they might still come together, but it would be a caustic rather than a conjugate point. I mean, could that happen? That's just so when geodesics cross. When they get together, that's a more general phenomenon in optics or whatever, that geodesics can cross, and there's not some discrete symmetry that ensure it. It's just more like a focusing term or something. that's a more generic phenomenon that can happen for geodesics. It's what happens for an entanglement when it's generic, or not generic, but anyway, but there's suitable matter that you can have causes.
Yeah, I'm afraid I'm not sure.
You should think of conjugate points as like the Riemannian version of caustics.
Yeah, so that they're not guaranteed by discrete symmetry.
The global picture is not so relevant.
So the two-sphere picture is a little bit misleading that way.
The two-sphere supports both a conjugate point and a global discrete symmetry, as you're saying. So it's a little bit misleading.
Okay, next.